Hello and welcome back to Calculus 1 section 5.2 on definite integrals. Last time we talked about approximating area under the curve, and we used left hand and right hand sums which had error, which is why it was called approximation, because it's not exact. And the idea was to, for a given function, make a couple of the rectangles, and then if you keep subdividing those rectangles into smaller and smaller, like thinner and thinner pieces between values a and b, each one of these little lengths here was delta x, and each point here was f of x0, f of x1, f of x2, and so on. So we had the heights calculated in the function, and the width was delta x, and we said that delta x was b minus a over n, which was number of rectangles. And then once we had that, we said that we can calculate the area by multiplying width by the function height, and we use xi, where I was the counter, right, to tell us whether we're talking about the first rectangle, second rectangle, third rectangle, right? So we kept track of particular rectangle we talked about by using the xi, where this I went from 0 to n and work its way out. So now what I'm going to do is I'm going to pick one of these, and I'm going to get the formula for exact area under the curve by making all of these rectangles infinitely thin. But if I make them infinitely thin, then I need infinitely many rectangles to fit underneath so that I can cover the entire area. Now, if the rectangle is infinitely thin, then there is no error, and which means that we can find the exact area by using that concept where we have infinitely many rectangles. Now, how do we build this? Well, if I take a look at this one particular rectangle, we know that we can calculate area of a single rectangle by taking whatever xi, right, in f times delta x, which would give us the area of one rectangle. So that's one rectangle when you multiply the height by the width, and the width is delta x. And then we said that if we have many rectangles, we can approximate the area. So we said let's add summation from 1 to some n, and that n is the number of rectangles. So maybe you want 5 rectangles, maybe 10, maybe 10,000 if you're coding this. I hope you already coded this. And when you plug in, when you add the sum, and this is I equals 1 on the sum, I equals 1. So now that's going to be many rectangles. Well, in particular n rectangles, that's how many. And now I want to exact area, so I'm going to send this n to infinity in the limit, and this is going to be infinitely many rectangles because n goes to infinity, right? and now this is equal to exact area. So as you can see, it's built up, right? We didn't make this stuff up. It is exactly built from, you start with one rectangle, then you put a summation in to add many rectangles, and then you send that n, which used to be a finite number of rectangles, maybe 5, maybe 10, maybe 10,000, right? You send that n to infinity, making infinitely many rectangles. Now, when you fit infinitely many rectangles between A and B, they have to be infinitely thin. Because if you, let's say your interval A and B is 2 and 7. 2 and 7 has the width of 5. 5 divided by infinity of rectangles, that means the width of each rectangle is practically 0. So now, this result is called Riemann sum, and this result calculates area under the curve as long as the function doesn't dip below x-axis, but we'll deal with that later. So I have Riemann sum which gives us area equals limit n goes to infinity, summation I goes from 1 to n of f of xi times delta x. And that's the Riemann sum to find area under the curve. Now again, we are using this for the curves where we can't use our rectangles and triangles and circles and geometry that we already know area for. So let's go and use that to find area under f of x equals to, I don't know, 3x squared minus x plus 9, whatever, on interval, what should we put here? Let's go 1 to 4. So interval 1 to 4. You can literally put whatever you want. Doesn't matter. Okay. So find area under the curve. You understand what that means. You draw the function if you can, and then once you have the function, you take 1 and 4, and then the function should be bounded between all of these. So what I can do is, let's say this is the function. I know it's not, but let's say it is. And then 1 to 4 and x-axis and the function, and that will be the area that we are looking for. Now, why would we look for area? We'll see application of this, very important, right? But some of the easy examples that you might associate with is how much rain did we have in October, right? It's going to be cumulative amount of rain. What's the amount of population that lives somewhere? What is the velocity given acceleration? So there's a lot of things. Oh, energy in physics, area under the curve. So a lot of things that you can compute with this, a lot of applications, right, that you can compute using this method. So now let's take a look at the way to figure this out. We start with delta x, and we know that's b minus a over n. So that's 4 minus 1 over n, which is 3 over n. And you can't change that. 3 over n is 3 over n. We are going to have infinitely many rectangles, so that n is not a number that you can plug in. So you have to leave it as 3 over n and deal with it as you go and work your problem out. Now, when you look at the formula up there, you already have a piece to plug in for delta x. That's just 3 over n. Well, now you need to work out xi's so that you can replace these x's by xi's, because they have to compute the function value at every x integer that we need to pick, or not integer, fraction, or whatever the division is. So to figure xi, think of it this way. You start at 1, you have a whole bunch of these divisions, and you eventually end up at 4. That's your a and b for the interval. Each one of these lengths over here is delta x, which we know is 3 over n in this case. So each one of these is delta x. And we know that these values, this is x0, this is x1, x2, x3, x4, x5, x6, x7, x8. So all of those values and now to go from x0 to x1 you add delta x. So x1 is x0 plus delta x, which is a plus delta x. To go to x2, from x0, you add 2 delta x, and that's a plus 2 delta x. To go to x3, we have x0 plus 3 delta x, because this is where x3 is, right? And you have 3 delta x's to add to get there. So that's a plus 3 delta x. It is quickly seen that the index matches the amount of delta x's you are adding, so we can exploit that into a formula that xi is always equal to a plus n delta, I delta x. So your index I, 1, 2, 3, 4, is the same as the multiplier for delta x to get to that location. So this is actually a formula along with delta x formula over here from last class. This is the formula now that we use for xi that we are going to plug in our f of x. So now f of xi is going to be what? 3 times xi minus xi plus 9. And now you will have that from here, you have that xi is equal to 1 plus I times 3 over n, because you plug everything in. Your a is 1, because your interval is 1 to 4. So your a is 1. You know your delta x is calculated earlier as 3 over n. So you'll plug that in. And now you will take these and plug over there to create f of xi as a function. So that's 3 times 1 plus, you can say 3i over n squared minus 1 plus 3i over n plus 9. So f of xi is equal to, and now I have to FOIL all of this mess and multiply by 3. 1 squared is 1 times 3 is 3, plus 6 times 3 is 18i over n. 3 squared is 9 times 3, 27 I squared over n squared, minus 1 minus 3i over n plus 9. F of xi is 3 minus 1 is 2, plus 9 is 11. 18i over n minus 3i over n is 15i over n, so plus 15i over n. And finally, plus 27i squared over n squared. So a little bit of algebra there to get our f of xi. Fun is about to begin. Lock the doors. Now we plug everything into Riemann sum so we can compute it. Remember what we did. All of this calculation here was to find what delta x is and what f of xi is so we can stuff them into the formula so we can compute and get a value at the end, like 7/2 or 128 over 3 or something like that, right? So now we plug all of that into Riemann sum. Riemann sum limit n goes to infinity, summation 1 to n of f of xi times delta x. So, and that's area, right? So area equals limit n goes to infinity, summation 1 to n, and now in parentheses here I have my polynomial 11 plus, well, we can put it in descending order, 27i squared over n squared plus 15i over n plus 11 times 3 over n, which is the delta x. That's a 15. Come on, eraser, you can do it. The obvious step is to multiply 3 over n. So we have that area is the limit n goes to infinity of the summation 1 to n, and now everything is going to be in a single one. 81i squared over n squared plus 45i over n squared, oh, supposed to be n cubed, and then n squared plus 33 over n. And then what we get to do? Well, now we are going to recall that the variable for the sum is I, not n, I. N is the variable for the limit. Because you see over here that this n goes to infinity, so the variable for the limit is n, and limit can't care less about i's. Summation has the variable I as the variable, and n is nothing, because, I mean, n is the end point where we stop, but the variable is, so n is a constant in the eyes of the sum, but it's a variable in the eyes of the limit. So we can split these into individual sums, and then we can kick all of the non-variable terms. So this is I equals 1 to n plus another summation 45i over n squared, I goes from 1 to n, plus summation of 33 over n, I goes from 1 to n. So we separate. Did I have any minus signs? Because, of course. See, I made a mistake. I gotta go and fix this. All of the minus signs in front of x. So where do we have those? I have the minus there. I have the minus. The minus is worked out there. No, it worked out actually, because I did use a minus sign in there. Minus 1 and minus, so it happened that it is 9 plus 3 is 12, minus 1 is 11. And then, yeah, okay, so minus signs. All right, fine. Cool. Now, what I said is we kick out all of the terms, like the terms of variables. So a equals limit n goes to infinity. And now for the first sum, 81 over n cubed has nothing to do with variables. And then summation of I squared going from 1 to n. Plus 45 over n squared is again not a variable for the sum, but I is. And over here, plus 33 over n, you kick it out of the sum, and only number 1 stays inside from 1 to n. So number 1 stays when you kick everything out. Cool. The next thing is to use the formulas which convert these. There are 4 formulas in the textbook that convert those sums into expressions with n, because those would be the sum of those expressions. So we have 81 over n cubed, and now I squared, I'll put it orange, is going to be n plus 1, 2n plus 1 divided by 6. Then we have plus 45 over n squared, and then we have the I, and that would be n plus 1 over 2. And finally, plus 33 over n times n, because summation of 1 is just going to be n. And now, look what we have. A basic limit from chapter 2. And you can just worry about front coefficients, because this is the limit that goes to infinity, so only the coefficients matter. The rest of the stuff, right, if the exponents are the same, the rest of the stuff doesn't matter. So I have 81 times 2, which would be 162 n cubed divided by n cubed, no, 6n cubed, and the rest you can throw in the garbage, plus 45n squared divided by 2n squared, and the rest can go to garbage, and plus 33 at the end when those n's cancel. Now you also see that all of the n's will actually cancel, and the only thing you have to worry about is calculating 162 divided by 6 plus 45 divided by 2 plus 33 divided by 1, if you want common denominator. But we can reduce this. 162 was doubled, right, from 81, so we can reduce this as 81 over 3 plus 45 over 2 plus 33 over 1. Now 81 is divisible by 3, you get 27. So this is actually 27 plus half of 45 is 22.5. So we'll have 22.5 and plus 33 at the end, so we don't have to drag the fractions. That's 82.5 units squared. Yay! We computed exact area for this curve, the exact area under the curve, but above the x-axis. So when you look at this, right, procedure, it takes a while to calculate this. Let's go a few pages back where we started, right? There's the statement of the problem. We compute delta x, then we work on a partitioning to compute xi's, and then we plug xi's into f of x to come up with f of xi. Work out that algebra, and then finally we have delta x and we have f of xi, and then we can plug everything into the formula, which is what happened right there. And in this one, right, we had, if you carefully, right, pay attention, you have your f of xi, and you have your delta x on the side. So both features are there, and from that point on, it's the steps of calculating all this mess to come up with the answer at the end. So once we plug everything in, we split the sums into 3 sums. We'll FOIL first, right, at 3n, distribute 3n. And then once all of that is done, we go and, we go and split the sums. Then we have these orange formulas. There are 4 formulas given in the book. Constant, I squared, and I cubed. Those are the 3 formulas given. And we used 3 out of, this n was supposed to be orange at the end. So you know it's coming from the formula. So that is there, that is there, and that is there. So those are the formulas from the book. Again, the proof for these formulas is in Calc 2, but then again, if you are not taking honors Calc 2, you're not going to see it. So yeah, but obviously these are sums. So split the sums and then kick out the non-I factors, and then use the formulas, and from that point on, you just need to take the limit. If you did everything correctly, all of the terms will cancel and you will just have numbers, because the limit will kill all other terms, so we don't care about them, and we'll just have values to add at the end. So it's a cool calculation, right? Should take about 30-40 minutes. Yes?
On the bottom, scroll down, when you substitute the orange, n plus 1, all of those, how did you get from, are you supposed to multiply them together? How did you get 162 n?
So the question is, what happens with the rest? Because when you FOIL this, you should get 6 terms. Why don't I have 6 terms? Why do I have only 1? Because all other terms will have a degree less than n cubed. Our denominator has n cubed. So only that the highest exponent degree, highest degree term will survive. The rest of them, the limit will kill them. If you have, this is from 2.5 on limits. If you have a limit n goes to infinity and you have some kind of n squared divided by some kind of n cubed, it's immediately 0. So when I FOIL all of this to get 6 different terms, as I am circling this, I might be using actually the one that you want to spot. So if I am to actually FOIL this, I should get 6 terms, but only the first term will be 2n cubed. Everything else would be n squared or less. And all of those terms will die in the limit, which is why I don't care about them. I only look at the highest power because I know that all of the other ones will be gone once I apply the limit. So what I did here is I said 2n times n squared is 2n cubed times 81 is 162n cubed. And I ignored everything else because everything else is going to produce terms that are less than n cubed. And when I divide them by n cubed, they were going to go to 0 in the limit. I did the same thing here. Yes, there is also 45n term. But 45n over n squared is 45 over n. And when you hit that with the limit, it's going to go to 0. So we don't need any of those terms. Now, sure, if you FOIL everything out and get all of those terms, then it's just going to be annoyed with writing because it's going to be, extra 7 terms to write in that line. And all of those right extra terms you wrote are going to go to 0. So, it's like pick your poison. Does this make sense? I see you guys are still not happy with this. Or maybe it's just the fact that it's, almost 4 p.m. and it's just, we should be done. But then the class. So let me give you a little pre-calculus. So x times x plus 1 times x plus 2. I am claiming that the only important thing here is x cubed and the rest is garbage. Actually, let's have it as a 2 over there. So here, 2x cubed. And the rest is garbage, right? Now, you would say, well, why? Well, first off, the first term tells me pretty much everything. The exponent tells me the shape of the function. Positive 2 tells me which way it's going to be oriented. And this is the largest term out of all of them because it's cubed. Now, if you want to write all of the terms, right, then you have your 2x cubed. Well, let's FOIL then in this case. There will be x times, we have 2x squared plus 4x plus x plus 2, which gives me 2x cubed plus 5x squared plus 2x. So now you see that when I FOIL the whole thing, I have that 2x cubed as the highest exponent, and the rest are lower exponents, and we don't care about them. Why? Because eventually it will be divided by x cubed, and then these guys will provide a 2, and the other guys over here would provide 0 plus 0. So anytime when you are getting a term that it's less than what you have in denominator, they will be giving you 0 in the limit, because limit goes to infinity, and that's why we do not have to care. We do not have to care. We can just take the highest term and be done. So now, that's here for the limit. Once you have the orange formulas in, all you care about is 81 times n times n times n, 2n, sorry. So that's 162n cubed divided by 6n cubed. When n cubes cancel, you have your 162 over 6. Same thing for the other two terms. And eventually all of this ends into 82.5.
Since there's no exam for this, how many questions would there be on the final event?
Why is that important at all?
No, I was just curious.
I can put 3 or 4. They cover beautifully all of the aspects of cover limits, they cover sums, they cover, right? We'll put 3 or 4. Is that enough? Would you like more?
How many questions is it?
Yeah, anywhere from like 12 to 15. So makes sense. I always get that question.
Well, no,
because the grade is the only concern, right?
Well, yeah, that. It's like in high school.
I've seen a research, someone sent me the research that new generations are doing better in school than old generations, right? So you guys are better in school than what I was when I went. But when you compare the quality of knowledge, actually, it's completely reversed. You have better grades, but you have less knowledge, which is scary, right? You know what I did last year? I took my exam from 2010 as a practice exam. And pretty much no one in class was able to do it. And that was just a regular exam. That's the curve that all of this stuff is getting easier and washed more and washed more and washed more. So you actually know less by having higher grades, which is scary. And then the research looks like that you guys are doing better than the older generations. And everyone sees that actually in the So I don't know where it's going to go. But let's see something else here. So we have this calculation, right? We have this calculation, and now it turns out that we can do something else instead. If I take the integral of the same function, what was the function? 3x squared minus x plus 9. 3x squared minus x plus 9 dx. And I put the limits, what were our limits, 1 to 4? And I put the limits on the integral, which is what we did not do last time. That's new. You guys have different calculation for the same thing. What's the integral of 3x squared? Well, you know that you are supposed to copy the 3, and integral of x squared is x cubed over 3, and these guys will cancel. Minus x squared over 2 plus 9x from 1 to 4. What's happening? We have now x cubed minus x squared over 2 plus 9x, and instead of plus c, we have this vertical line, which is read as computed at 1 and 4. That's the way you read this line. And the way you compute this is you plug in the 4, and then you subtract, plug in 1 into the whole function. So we have 4 cubed minus 4 squared over 2 plus 9 times 4, and then 1 cubed minus 1 squared over 2 plus 9 times 1. So I plugged in 4 into the function, and then I subtracted the function plugged in 1. So 4 cubed is 64, minus 16 divided by 2 is 8, plus 9 times 4 is 36, minus 1, minus half, no, plus half, lies, plus half, and then minus 9. So 64 plus 36 is 100, minus 1 minus 18, plus 1 half. Because we have minus 8, minus 1 is minus 9, minus 9 minus 9 is minus 18, and then you have the half. 100 minus 18 is 82, plus 1 half is 82.5. Oops. 82.5. Hey, we had 82.5 before. So now, which calculation is better? The second one, right? Remember how you had a way to calculate the limit, a derivative using limits with the f of x plus h minus f of x? Remember that? Mm-hmm. Yeah, well, this is the equivalent thing for integrals. Right? The long way for integrals, and then the short way for integrals. And now you have a choice. Which one do you want to use? Do you want to use the first one or the second one? This is like, go to the eye doctor and goes, okay, what's better, A or B? A or B. Sometimes they use 1 and 2. Right? So we don't use this method anymore. Right? This method is about 180 years old, right? And Riemann figured out all of that stuff, obviously, wrote it down on the paper, but then he figured out integration right after that. So we don't have to bother with this long integration because we have the compact form. But this compact form requires you to know 4.9, and instead of putting plus c, you have to put this vertical line with limits, And this is what it's called the definite integral. So now, when I write the definition over here, well, it's not a definition, it's like a formula. We say that the limit n goes to infinity of summation 1 to n of f of xi delta x is actually equal to the integral a to b f of x dx. Yes. It is I equals 1. So instead of doing the whole thing that we did with Riemann sums, instead we can just do a little integral between two values. Now, to compute the definite integral, oops. To compute the definite integral, we use integral a to b of f of x dx is equal to any antiderivative f of x. That's the one that is supposed to have plus c. But we don't put plus c, we put line, and then we say f of b minus f of a. And that's the second large cloud. We're going to see this again written in 5.3. So now, if you go back to the problem that you had earlier with the square root of x, which was from 0 to 5, and you wanted to compute area under the curve, and we use all of those approximation methods, now you know that you can just run integral 0 to 5 to find area, right? Integral 0 to 5 of square root of x dx. And as long as you can integrate, you should be fine to solve this without going through all the hoops of the calculation. Yes?
Are you always given A and B?
Yes. Because, for instance, one of the project's questions that I don't think I put on yours is the rainfall problem. And they give you the function for the rainfall, which you actually observe in sciences and you figure it out. And then your A and B would be the months, because the rainfall function is for the whole year. And 0 to 1 represents January, right? 1 to 2 represents February, because it takes the whole month of rainfall. So once you do that partition, then you can bunch up a couple of months together, right? So you will go 0 to 3 for the first 3 months, right? January through March. And you will know how much rain you had. Now, these are the things that scientists actually compute, right? Because those are important to plug into the further functions that will predict the weather, so that the people can come on TV and say, tomorrow we have 70% of chance of rain, right? So A and B are given to you, and the answer for these definite integrals is always a number, right? So what we had in 4.9, which we call indefinite integrals, those integrals have a function as the answer, and then plus c. If you're given a point, you can compute the value for c. For definite integrals, you have the limits, a and b, and you have a function. Once you integrate everything, you get you get this. So let's go and see this problem. We learned last class that we are supposed to write x to the 1/2 and then we're going to add 1, so x to the 3 halves divided by 3 halves, and instead of plus c, we're going to put 0 and 5. So now that's going to be 2/3 when you bring it from denominator up. 2/3 x to the 3 halves from 0 to 5. So now that's 2/3, and you have 5 to the 3 halves minus 0 to the 3 halves. Now 0 to the 3 halves is 0, so we don't have to worry about that. The only thing that I need is to figure out what 5 to the 3 halves is and multiply that by 2/3. And we should get a number, if you remember the numbers from the last class, we should get a number that is between 6.1 and 8.3, if I remember well. So let's take a look at this calculation. We have 5 raised to 1.5, and then times 2 and divide by 3, 7.4536, blah, blah, blah. Okay? Hey, that is between the two values that we had last time. So from 5.1, we have 6.1 less than 7.4536 less than 8.3. So one approximation was undershooting the area, the other one was overshooting the area, with the true area being in between. And you'll see that if you took the average of 6.1 and 8.3, it will give you 7.2, right? 7.2 is close to 7.45. So you could have taken the average and get close to the true area. But again, if you do left sums on a 10,000 rectangles, you're going to hit all of these digits for your approximation, because they already get to be too small. So we started by approximating, then we expanded to infinity of the rectangles, and then we finally landed into, we can replace all of that mess with simple integration and then calculate the limits of those definite integrals and be done. Now, it's important to understand that the pitfall of the problem computing the area is that function must be above x-axis. If any of the parts of the function dip below x-axis, you are going to create negative area. It will subtract from the area on top, and you will get the wrong answer. So here is the problem to illustrate that and the way to fix it. Now, start this problem because it shows up on a final both as a problem and as a concept. In terms of a question, is area under the curve and definite integral always the same thing? In which case you have to say no, because, and here is the problem. So let's say you want to find the area under sine x dx from 0 to 2 pi. Right? And you just say, I could just do integral, right? So the integral of sine is negative cosine from 0 to 2 pi. And now if you have negative cosine of 2 pi minus negative cosine of 0, well, cosine of 2 pi is 1, so you have a negative 1. Minus and minus gives you a plus, and cosine of 0 is 1, and you get a big fat 0. And you know that's wrong. You know it's wrong. Why do you know it's wrong? Because if you graph sine function, you can color, right? There is area to color, so it's not 0. Let's graph sine function from 0 to 2 pi. Whoop, there we go. 0 to 2 pi. See, there is area for me to color. So all of this is area to color. And if I color the area, that means that area definitely not 0. The calculation gave us 0. So what's the problem? This is what we are going to write now in blood. And remember, if the graph dips below x-axis, value of the definite integral is not equal to the area. Now, those concepts are extremely important, guys, especially if the integral is to give you energy or something that, you can make your day go bad if you don't do it right. Explosion is a release of energy. You don't want to mess with that stuff, but the battery holds energy as well, right? So, good concept, bad concept with the same, good outcome and a bad outcome within the same concept. So this is why you really want to be proficient with these things. Yes?
How come you can't just take the absolute value of it?
That's the way to fix it. Very good. So the next thing is, how do we fix the issue of integral of sine x dx from 0 to 2 pi? Well, you need to know exactly where it dips below, and it dips at pi. So we are going to use a property, which I haven't told you yet, but I'm going to write it now, that allows us to split the domain, and the integral will still. So here's the property that we need. And the property says integral a to b of f of x dx is equal to integral a to c f of x dx plus integral c to b f of x dx, with this c being in between a and b. Now, this property will be back in Calc 2 and, later on. So now, this property allows me to take my sine function and break it into the integral of 0 to pi sine x dx plus the absolute value, as Mel noted, which would give us the positive outcome. And now we should, right? So technically, what is this absolute value? This absolute value is going to bump this one up, and you'll have two bumps like that rather than having one on the bottom. That's what it does. It just brings it to the positive side. Now when we run our integration, which is still negative cosine, and compute everything, we should have a good result. So negative cosine x computed from 0 to pi plus absolute value of negative cosine x computed from pi to 2 pi closed absolute value. So that's negative cosine pi minus negative cosine 0 plus absolute value negative cosine 2 pi minus negative cosine pi closed absolute value. Cosine of pi is negative 1, so we have negative 1. Minus and minus gives me plus, and then this is a 1, because cosine of 0 is 1. Plus absolute value, cosine of 2 pi is 1, so the whole thing is negative 1. Minus and minus gives me a plus, and then cosine of pi is negative 1. That's just a lot of chasing around. So you have 1 plus 1 plus absolute value of minus 1 minus 1. This is 2 plus absolute value of negative 2, which works out to be 4. And this is one of the favorite calculus calculations that I have, because sines and cosines, right? You're expecting terrible things, right, in terms of divisions of pi and everything else. Area under the sine curve is 4. Also under cosine curve is also 4, which is really awesome. Really awesome. So now we know that the area is not always same as the value of the integral. You have to be careful and make sure that your function is always positive, and if it's not positive, that negative part needs to be bumped up, right, separated from the rest of the problem. You bump it up with absolute value. Once you apply absolute value, it's the same piece, just symmetrically above the it's above the line, and then cool. Let's just solve a few of these and call it a day. So what about the integral from 3 to e squared of 2 dx over x? How do we integrate this? We start by kicking out the 2. Very good. And now we just have 1 over x dx. 3 2e squared. What is the integral of 1 over x?
ln x. No. It's like ln absolute value.
Yes, absolute value. Good. So 2 ln absolute value of x. And then instead of plus c, we put 3 and e squared. Is a good one. And then we have 2 ln of e squared minus ln 3. Now note that I lost absolute values because e is squared, it's positive, and 3 is positive, so I don't need absolute values. That's 2 times, when ln and case cancels, you just have a 2 minus ln 3. And that's it. That's the exact answer, right? You can go get decimals. No one cares about them, but you can. So you will plug in the upper limit first, which is f of b, and then f of a, lower limit, and then you will calculate. Now guys, this particular calculation is on the list of important things for Calc 2, so make sure you know it. Bye.